Let's continue with Z-transform examples. This is from Rose-Hulman University's YouTube channel, so follow the link please. In this example, we are given h of z, and as you know, h of z is the Z-transform of h of n, the impulse response of a LTI system. So the Z-transform of a h of n is h of z. H of n is called the impulse response, and h of z is called the transfer function. We are given the transfer function h of z in negative powers of z, and we are asked to find the following: the pole and the zero diagram, the impulse response. Here it says stable and here it says causal. Let's find out what's happening over here. The pole and zero diagram first. In the pole and zero diagram, let's start with h of z, but we are given in negative powers of z. What we need to do is we have to multiply with z squared over z squared, which is equals to 1, so that we can convert a negative power into a positive power. Only when we do so can we then simplify and allowing us to find the poles and zero. So if you work it out backwards, this is the numerator and this is the denominator, and you will see that now we can identify the poles and zero. How do we identify the poles and zero? Well, if z is 0, 0 multiplied by everything is 0. So z equals to 0 is a root of the numerator. Similarly, z equals to minus 0.25 is a root of the numerator. The root of the numerators are called the zeros of the transfer function. So let's find z equals to 0, z equals to 0.25. Where are they? They're here. Z is equals to 0, z equals to minus 0.25, because it is minus 0.25 plus 0.25 that will cause the numerator to be 0. Similarly, z equals to minus 1.4, z equals to 0.6 are the pole. Minus 1.4, 0.6. So minus 1.4 plus 0.6. So this is the pole and the zero diagram. So the trick to do this is when we are given negative powers of z, we must convert it into positive powers of z, do factorization on the numerator and the denominator to identify the pole and zero. So when we draw the pole and zero diagram, we'll first draw the complex plane. So this is the real part of z, this is the imaginary part of z. We'll also draw the unit circle, and the unit circle is the circle of radius 1. So this is minus 1 here, this is plus 1 here, on the bottom is minus j, and on the top is plus j. So we draw the unit circle followed by the poles and zero. Okay. Now we can go to the stable impulse response as well as the causal impulse response. In stable impulse response, we need the ROC, the region of convergence, to include the unit circle. Only when the ROC includes the unit circle would the system be stable. Alright, how do we do that? In this example, what you do is that from this form, we'll go into the partial fraction expansion so that we can identify individually a form that is suitable for the lookup table. What we need to do now is to identify from this form in the lookup table whether it is a causal sequence or an anti-causal sequence. In this particular case, this needs to be causal, so that the ROC, so 0.6 is the pole, this is here, the ROC needs to extend outwards. So this is a causal sequence. Now the other case is we have a pole at minus 1.4. Now the ROC needs to extend inwards so that the ROC will intersect with the other guy, so that the unit circle will be part of the ROC. When it extends inward, the idea is that it becomes an anti-causal sequence, like here in the bottom. The expression of the Z transform is identical. The difference is whether its ROC is outside the pole or inside the pole towards the origin. So now we know that this is the anti-causal sequence, this is the causal sequence, and we can write the answer here. So the numerator 0.4250 comes out, and then we are just putting this expression here. A is 0.6 NUN. For the anti-causal, the numerator constant goes out, 0.575, and then we will plug in minus sign on the outside. Now A is minus 1.4, so this is minus 1.4 for the A, and then we have N here, and then U of minus N minus 1. So notice that, please be careful, this A is minus 1.4, so it is minus 1.4 bracket to the power of N, U minus N minus 1. This minus comes from this minus, the first minus sign here, so minus 0.575. Let's look at the answer. So this is the answer. This is the anti-causal sequence, because we can identify that uses U minus N minus 1. This is the causal sequence because we can identify UN. So this is the final answer for this, finding the time impulse response representation of this HC for a causal, no, not for a causal, for a stable impulse response. So to recap, for a system to be stable, it must include the unit circle, and now we have a choice of selecting the pole N0 for these two poles. 0.6 must have the ROC extending outwards so that you have a chance to touch the unit circle. Minus 1.4 pole, the ROC must extend inward to touch the unit circle. The intersection is the ROC, and when it extends inward, it is anti-causal. For 0.6, when it extends outward, it's a causal. So that is why we have these two cases here. Now, in the last part of the question, instead it asks us to find a causal impulse response. To find the causal impulse response, then what we do is that instead of selecting the anti-causal part, we'll select the causal part. So the answer is this. We have the causal part, for both of this expression. We use the causal lookup to transform from the HC to HN. So this is the causal part, 0.57 minus 1.4 to the power of NUN, and this guy is also causal as before. Now what you realize is that in this particular case, because the pole is outside the unit circle and this pole also extends outside, only the intersection between these two will be the correct ROC. Therefore, the unit circle is not part of the ROC. Now what happened? 1.4 to the power of n will become bigger and bigger, even negative 1.4 as n goes large. So h of n goes to infinity when n goes to infinity. So that's the problem, or when the ROC does not include the unit circle. Alright, I'll show you my working. So in this example, this is my working, and in my working, I'm going to use, again I use MATLAB just to verify, and again I'm going to use residual z over here, and in residual z, what you realize is that I must express my vectors representing the coefficients of the numerator and the denominator as negative powers of z. So this is 1 and 0.25 here, and the denominator is 1, 0.8 and minus 0.84, which is here. and then by substituting into residual z as the parameters numerator and denominator, I get rpk, and my r is this, and my p is this, and my k is nothing. So remember, when you use rpk, the first r1 goes to here, so 0.575. The first p goes to here, 1 minus 0.425 z minus 1. The second one is r is 0.425, goes to here, and the other p is 0.6. Oh, sorry, I make a mistake. This is 0.575. This guy is minus 1.4. This guy is 0.425. This guy is 0.6. Okay, scratch that. So this is the correct values, and when I put it here, this is the final answer. Once I have in this form, then I can perform a lookup table depending on my ROC. Okay, so that's why in the first case, when I have the ROC to include the unit circle, the first expression is an anti-causal sequence, second expression is a causal sequence. Now, in this anti-causal sequence, you would be thinking minus 1.4 to the power of n, but because this is u minus n minus 1, n exists only from 0 to negative infinity. Oh, so what happened is that then, n equals to from minus 1? Go and check. In fact, n start from minus 1 because of this unit step delay or advanced by 1. Anyway, what you realize is that because n is getting more and more negative, therefore minus 1.4 to a power of to a negative power, this becomes smaller and smaller, and hence this will become smaller when it goes to negative infinity. This guy only starts at n equals to 0 and will become smaller as n equals to positive infinity. So the whole thing becomes 0 at both end of the time index n, and therefore it is absolutely summable, and therefore the system is stable. Now, in the next slide, I show you how to do the same problem in positive powers of z. So I know that I've showed it to you in a negative power of z. Let me show you in the positive power of z. So how do we go from negative power of z to positive power of z? Is to multiply on the top by z squared and the bottom by z squared. So this guy is multiplying by 1. The numerator becomes z squared plus 0.25z. The denominator becomes this expression. And then, if you remember, the plus transform, we are in positive power of s. So this positive power of z. You realize that if you use the residual, you must use residual now instead of residual z. Okay, so now, when you solve in positive power of z, there is a trick. We will express h of z divided by z, and then we will perform the partial fraction expansion of the right hand side. This is because later on we'll need to move the z to the right hand side for the lookup table to that's the typical lookup table we are used to. So the numerator power of z is 1 and 0.25. Where is this? This is here, and then the denominator is 1, 0.8 and minus 0.84, which is here. We use the residual. So please remember, this is using RPK equals to residual. There is no z, okay? Not z. That's residual, not residual z. We use of numerator and denominator because we are using positive powers of z in the expression. Then you get this answer and we substitute in. When you substitute in, we move the z to the right hand side and we'll get it in this expression. K is equals to 0, and therefore now the answer is the same. Okay, so this is the trick using positive powers of z to solve the same problem. And that's it for this question. Thank you very much.